Hello, my name is Katherine Starcher, and this is Lab 3 of Physics 2212, Magnetic Field of a Permanent Dipole. The goal of this lab was to determine the distance dependence, or the relationship between distance and magnetic field, of a bar magnet. We then compared the prediction for the distance dependence based on calculations with the Biot-Savart law to measured findings done using a permanent dipole magnet. Important principles to complete this lab were the Biot-Savart law for magnetic field of a bar magnet, as well as the superposition of magnetic fields both on and off axis. To set up the bar magnet properly, you must first find Earth's magnetic north-south axis. To do this, simply rotate the magnetometer, or your phone, until the x component goes to 0. Put the ruler along the bottom of the phone. This is representative of the east to west axis. The bar magnet should be placed at the end of the ruler. At this point, you should check to see if the net magnetic field at the top of the magnetometer is correct to ensure it's taking accurate measurements. For France, this value is approximately 48 microtesla. The next step is to find the magnetic chip inside of the phone, that is, approximating the magnetometer values. This will be the point at which all values will be measured from here on out. To find the horizontal component, find the position where x is a max and y is a minimum, and place a piece of tape horizontally across the phone. Next, flip the phone to be horizontal and move it up and down along an axis to find where y is a max and x is a minimum. Again, place a piece of tape vertically at this location. The upper right intersection is where the chip is located. I then found the distance from the bar magnet to the magnetometer chip for each of the given Bx values. Bx is the x component of the magnetic field, and I found the distances at 20, 70, 120, 170, and 220 microtesla. The graph on the right shows the relationship between the natural log of the x component of the magnetic field versus the distance, ln of r, that the magnetometer was from the bar magnet. It gives us valuable information because the slope of negative 2.9488 is the value of n, which should be approximately negative 3, and the y-intercept of negative 14.35 is the value of ln of k, which we will use later to calculate mu. To calculate mu, I use the distance dependence formula, magnitude of b bar equals kr to the n, as well as the before mentioned values. I found that k is equal to 5.85 times 10 to the negative 7, and this allowed me to calculate the value for mu of 2.925. To find the off-axis measurements for the off-axis magnetic field, I found the distances where the net magnetic field was roughly 100 microteslas in both the x and y direction, and recorded each of the magnetic field components at that distance. I used those values for the off-axis perpendicular magnetic field as well as those for the on-axis field to create a function that calculates the magnetic field using the Biot-Savart law. In this code, you can see the vectors representing the on-axis magnetic field that are r-axis and b-axis, and then those representing the perpendicular. Later, I used my code to draw an arrow representing the magnetic field 45 degrees from the axis, in between the on-axis and the perpendicular magnetic fields. In this slide, you can see the visualization of the code with the orange arrows representing the on-axis magnetic field, the blue arrows representing the off-axis perpendicular magnetic field, and the magenta arrows are 45 degrees from the axis. The small white bit in the middle is representative of the bar magnet. As you can see in the previous slide, the measured and predicted values from the computational model of the magnetic field at 45 degrees do differ greatly by roughly 0.01 microtesla. This could be because of nearby electrical equipment or accidentally adjusting the smartphone, or just inaccuracies with the magnetometer in general. What if I hadn't oriented the magnetometer to compensate for magnetic north? If this were to happen, the y component would be incorrect and the calculations we made to adjust the y component would need to be changed. Lastly, what if I stuck two magnets together and ran the experiment again? The magnitude of the net magnetic field would double and be much larger.